Okay guys, so this is class number 7 and we are continuing our topics. And in the previous classes we learned about two main things and also about vectors and matrices and inverse of the matrix. Here we are. I have to make it smaller. So, and I uploaded part 1 of the notes on the Blackboard, so you can see it, okay? And how to deal with the elements of a matrix and the linear dependent and linear independent matrices. That the linearly independent matrix gives you the full rank matrices, right? The rank of the matrix and the determinant of the matrix and also inverse of the matrix, okay? So here we are. And now let me move this here and move this one here because I want to make it bigger and a little like this, okay? So if you remember in the previous class we said that D is equal to, let me use recording, yes, D is equal to or matrix A is equal to 1, 3 and 3, 4, 5 and 9 and 8. That's right. So what is our matrix? It's a 3 by 2 matrix. Now if I say the inverse of this matrix, what I'm gonna get is a matrix must be square, because inv command in the Matlab is for the square matrices. So what happens if our matrix is not a square? So the command for that is the pseudo inverse. Look at here, pseudo inverse matrix, pseudo inverse matrix. You're gonna see pseudo inverse matrix in the courses like the robotics guys. So ME596, and you're gonna deal with the pseudo matrices in the non-square matrices. So the generalized concept of the matrix inverse is pseudo inverse. So pseudo inverse can do both inverse and square and non-square matrices. In particular, for when matrix is not the square, you will eventually see this kind of matrices in robotic-based courses. So we use pinv a command to calculate the pseudo inverse of matrix. So, and if this is our A, that's right. If I say P is for pseudo, because pseudo is starting with the P letter, that's right. Pinv means pseudo inverse of the A, you're gonna get this. Understand? This is the pseudo inverse of the matrix. How we calculate that, you're gonna learn in the ME596 analytically. So forget how we calculate by hand because it's too much in the level of Matlab course. So look at these matrices. So if I say A is equal to, I'm talking about these matrices, guys. Okay, A is equal, let me make it a little bigger. Okay, if I say A is equal to 1, 0 and -4 and 6, this is 2 by 2 matrix. But if you say Pinv of A, it's gonna give you this number. Now if I say Pinv of A, it's gonna give you this number. So see, the result is the same. So the pinv is generalized format of the inv command. So if I say B is equal to 1, 3, 2 -2, 6, 1, okay, this is a non-square matrix that has 2 rows and 3 columns. So what you're gonna do, you're gonna say pinv of B. It's gonna give you 3 by 2 inverse of the matrix, okay? If you say 1, 3, 2 -4, 4 and 5, 0, 1 and 1, 4, 11 and -10, okay? This is 4 by 4 matrix. So if you say Pinv C means pseudo inverse, gonna give you this kind of things, right? So the inverse of this gonna be 3 by 4. Oh, this is 4 by 3, so it's gonna be 3 by 4. So if you use the inv of C, what do you expect to see? Obviously error message because the matrix is not the square. And finally, if you say D is equal to 1, 3, 4, 6, and 10, 11, 23, 11, 23, this is 3 by 2, so P inv of D gonna be 3 by 2. So guys, now look at this. If I put the last row as 0 and 0, when we had the square matrix, we know that this matrix determinant is how much? Is 0, that's right. So when the determinant is 0, you're gonna have the inverse matrix of unknown, infinity, that's right. So suppose this is your new D, because now you see that this matrix, the rows are linearly dependent. Remember I talked to you in the part 6 and part 5 in the YouTube link, that's right. So let us see if the same rule, if it is valid for the pseudo inverse, okay? So the pseudo inverse is not valid anymore, okay, understand? So and now we got the difference between P A and inv A, because they are the same, because the matrix A is the square matrix. Now matrix eigenvalue and eigenvector. Guys, this is very important, super important topics in the dynamics and control, and in too many fields of engineering actually. Eigenvalue problem. Eigen is a German word, means a specific value. So eigenvalue means a specific value, and eigenvector. The simplest example that you feel, suppose that you're on the airplane and the pilot is igniting the engine. When you see a voice like starting from 0 velocity of the engines, and some certainty of the velocity of the engines, you feel a shock like that, right? That's in the vibration course, we name it as the resonance, okay? So in eigenvalue and eigenvector, for any large scale system, I'm going to give you the natural frequency that you're going to feel that vibration. In the robotic we do have, in the control we do have. So eigenvalue, so in nonlinear control we do have, because if you go to grad school, we're going to be linearizing the nonlinear dynamical system around the equilibrium point to the linear system, and based on that we have to calculate too many things, okay? So eigenvalues of that, so to determine the stability or instability of the given system around the equilibrium point. So this is super important things that you have to know in MATLAB, because you're eventually gonna use it. Matrix eigenvalue and eigenvectors recording this, okay? So eigenvalue and eigenvectors undoubtedly play critical roles in many courses and research topics. In particular, you will eventually need to deal with these at SDSU, San Diego State, ME330, ME530, ME696, and robotics, ME596. So you see, 1, 2, 3, 4 courses. So we calculate the eigenvectors of a matrix given A through the following command. Okay, let me go to MATLAB and teach you first. So guys, I have to close it. Okay, so suppose that you have this matrix. So you have a given matrix A, and the A is 1. Now you know how to deal with the matrices, right? If I say calculate the eigenvalue of this, it's going to be SI. This is unity matrix. Unity matrix in the this is going to be EI. That's right, in the MATLAB. Minus A is 0. Determinant of this 0. Now you know what's determinant and two more things, right? So if you do that, SI gonna be S multiplied by I, because this is 2 by 2, gonna be this matrix, minus A, 1, 2, and 3, and 4. Okay, this determinant is 0. So what you get is gonna be S, I'm multiplying the scalar inside the matrix, 0, 0, and the S, that's right, minus 1, 2, 3, and 4. Okay, 0. So finally what you get is, if you subtract this matrix from this matrix, you're going to be S minus 1, minus 2, minus 3, and the S minus 4. See that? This is subtract, as I taught you previously. This is equal to 0. So we know that I taught you the determinant of a 2 by 2 matrix is diagonal elements minus non-diagonal elements multiplication. So we're going to be S minus 4 in S minus 2 and minus in 6, because minus and plus is 0. So if you simplify this, expand this, is going to be S2 minus 3S plus 2 minus 6 is 0. And you get S2 minus S squared minus 3S minus 4 is 0. So now you have two eigenvalues because it's second order equation, that's right. So you're going to have S1 is minus B 3 plus minus B squared 9 minus 4 AC. Gonna be 4 in minus 4 divided by 2A. When I'm talking about the ABC, remember from the high school, I'm talking about this. This is A, which is 1, B is minus 3, and C is minus 4. That's right. Remember, if you have such an equation, this is a general statement if you forgot in this level. So you have x1 and 2 is equal to minus b plus minus b squared minus 4ac divided by 2a. I'm just doing exactly here. So your b is minus 3. So minus minus plus 9 minus 4 in ac. Your a is 1 and the rest. Okay. So what you're going to get is 3 plus minus 9 plus 16. That's right. Divided by 2. And what you get is 3 plus minus 25. That's right. Divided by 2. Or 3 plus minus 5 divided by 2. So you're going to have two eigenvalues. So when you go to vibration curve, we name it two natural frequencies. Okay. When we go to the nonlinear control problems, okay. So we're going to have the Jacobian matrix roots to judge about the stability or instability of a given system. Understand? So when you go to robotics and the same and so on. Okay. So we're going to 8 divided by 2 is 4 and minus 2. So these are the eigenvalues of the system. Okay. For a vibration system, this is a joke. This sucks because we cannot have negative eigenvalues, right? But when I'm dealing with the nonlinear control course, if you go to graduate school, if you see that the eigenvalue of this linearized matrix is gonna be positive, means that your system is unstable on the Kuban point. Okay, you're gonna see it later, but here I'm just teaching you how to calculate in Matlab. Okay, so now we got that. This is by hand, but you have to learn how to do it by Matlab. Okay, and here we go. Okay, so as I taught you, you have to use by hand. You have to use this equation: SI identity or unit matrix minus A. I is identity matrix, which we defined above and I learned in the previous classes. Then you need to solve for a set of linear equations for obtaining eigenvectors. Matlab provides a simple command as follows. So this is a command. So command is this. I'm saying A is what was that here? 1, 2, 3, 4. Okay. Our A is 1, 2, 3, and 4. Okay, you got it. Now Matlab says, see, this is the command. It is bracket VD is equal to eig A, means eigenvalue. That's right. So this gives you eigenvalue and eigenvector. So this is eigenvector. Okay. This is one column, this is eigenvector 1 and eigenvector 2. And these are your eigenvalues. So here it is minus 3 point, and let me see. Probably I have done a mistake here, huh? Why my answer is different from this? It's positive, negative, but I don't know. 1, 2, 3, 4. Let me double check, guys. Oh yes, guys, I have done a mistake here. I don't know why. I'm getting older, probably. This is 4. Where I put 2. Okay. If that is 4, so this is gonna be minus 5. That's right. And it's gonna be 4 again. Yes. And this is minus 5. And it's gonna be minus 2. And so on. That's right. So let me redo it. So just stupid typo. So it's gonna be 5. That's right. And it's gonna be 25 minus 4, and this is 2, guys. And it's gonna be 5 again. It's 25 plus 8, guys. And again, it's gonna be 5. That's right. And it's gonna be 30. How much? It's gonna be 33. So, and now if you do that, it's gonna be 5 plus I don't know, 5.8, like that. So, and you get those results. What are those results? Let me double check. This is ballpark value, so yeah, minus, so this is probably 6, like that. It's gonna be 5.32, and the other number is how much? Minus 0.3, yeah, almost. Minus 0.37. But again, this is positive or negative, so I had a typo here. You get it? So you see that this natural frequency, or the eigenvalue of the Jacobian matrix, so one of these positive, negative, it can be done this. So see, you saw that even for this 2x2 matrix, I had a typo, stupid typo. So what I'm gonna do, I'm gonna, if you say you have this matrix, because suppose the any dynamical system, large scale systems, they're gonna have a high degree of freedom system, say 50 degree of freedom system. So you're gonna have 100 matrix of 100 by 100. So good luck for calculating by hand. So that's why if you go to a large scale systems, say it is, I don't know, n by n, you have to use the command in a Matlab. Actually, these days nobody does the calculation by the hand, because that sucks. Understand? So, and this is the matrix inside. Understand? So and the eigenvector, what is, so we understand what is the eigenvalue, okay? So we got the eigen. So, but let me show you. So, but these are the eigenvectors, okay? These are the eigenvectors. So what are the eigenvectors? Eigenvectors tells you, based on the natural frequency that you get, first natural frequency or second natural frequency, how your system moves. Okay, I don't want to go too much detail, but for the first eigenvector, it says that if this is your car, the front of your car goes up, but the rear of your car goes down. It's very interesting, that's right. After passing the bump, your car can experience this, or as it is. But the second eigenvector means the both of them, they are moving at the same direction, going up, going down, going up, going down. Okay, so I don't want to go too much detail on that, but we know how to calculate eigenvectors, right? So, and this is the command eig, that's right. So, but if I say, guys, look at here, if I say A is solved eigenvectors, A is 1, 0, 2, I'm talking about this, 3 by 3, okay, and 909, 1, 2.4, 0, 0, 1. It is a 3 by 3 matrix. So if I say Eig, only Eig, I type this command, okay? It only gives me what? It only gives me the eigenvalues. Understand? Here is 1, 1, 1. Okay? But if I type V and D is equal to this, it gives me eigenvectors. Okay? First eigenvector, second eigenvector, and third eigenvector. And what? The eigenvalues. 1, 1, 1. Understand? So for this matrix B, okay, is 1, 0, 2, 99, 100, 24. Oops. Okay. 24 and 0, 60 and 0. If I say the same command, eigenvector B. Okay. So it's ridiculous because your eigenvectors here are imaginary. So how we translate imaginary eigenvalue? You have to go for the nonlinear control course and how to linearize around the Jacobian matrix. And these are the eigenvalues, but this is funny because we don't have, in reality, we don't have imaginary motion. Okay. So, and part C, say your C is 1 minus 2000, 2, and 99. I think that you can hear the bird singing because of the eigenvalue. Thank you very much. Okay. So if I say again the same command, eigenvalue of C, you see that again we get imaginary things. Okay. It's good. I'm teaching in a romantic environment. And the D is 1.2, 3.4, 0. See, I'm going 4 by 4 matrix. Minus 99, 16, 24, and 1, and 0, 1, 1, and 32, and 4.2, 3.2, 10, 100. This is 4 by 4 matrix. So, and what you get? Again, your eigenvectors and eigenvalues. Okay. So, and part E. So E is 5 by 5. It's just practicing. 0.12, 0.12, hold on guys, it was too much noise. 0.34, 0, 56, 10, minus 9.9, 1.6, 2.7, 1, and 450. The next line, 0, 1, 1, 3.5, minus 300, 4.2, 3.2, 110 minus 100, 45, 56, 320, 10.66, minus 200 and 56. This is 5 by 5 matrix. So if I use this as for eigenvalue of the E, this is the eigenvalues and this is eigenvectors. Okay. So, and it's recording. Yes, it's recording. Now, having everything in the hand, now we can go and start solving a set of linear equations. Okay. After knowing about matrix manipulation, now we have enough tools to solve a set of linear equations and look at this problem. So let me do it here. Okay, guys. First, so now if you have a set of equations ax plus by plus cz is equal to e, and the fx plus ky plus lz is equal to m, and nx plus ox plus pz is equal to, I don't know, w. So now you can write this in the format of matrix, guys, to find what? Unknown variables or parameters x, y, z, x, y, z, guys. That's right. It's going to be a, b, c. See, a, b, c. This is how we multiply the matrix summing. There's a, b, and z. That's right. F, k, l, f, k, l, and n, o, p. This is equal to what? This is equal to e, m, and w. So, on the other hand, if I name as capital X, X, Y, Z, that's right, and if I say capital R as right hand side, M, E, M, W, and if I name this matrix as A, I can. Now I can write the equation of this AX is equal to R. Yes or no? Obviously yes. But we are not stupid to say X is equal to R over 8. This is a joke. You are dealing with the matrix. So what we're gonna do, we're gonna multiply from left hand side everything by inverse of A. It's gonna be inverse of R. From linear algebra, guys, we know that this is equal to how much? You tell me. Yes, it is identity matrix. So what you get is X is equal to A minus R. Yes or no? Obviously yes. Okay. So now with the Matlab we can do that, guys. So in the Matlab, as you see, I did the same. This equation number 10, and then I wrote it as a matrix and vector form. Then I multiplied the both sides by the inverse of this matrix, right? So, and now by inverse of that matrix we can calculate our things. Okay. Now suppose your A matrix I was talking about is 1, 3, 5, 1, 3, 5. That's right. And your and 9, 0, minus 1.55. Oh, this is minus 1 only. Okay. And 55, 19, and 100. That's right. And B, which is our capital R, here is 1, and this is a column. That's right. I taught you how to write a column. That's right. Semicolon. And 16, the right hand side of the equation. See, I mean this is B or our R. That's right. I'm saying B. That's right. Is a column. That's right. You see, this is a column. And this is your A, 3 by 3, and your B, which is this right hand side. Now I can, let me show you. Now I can say that I'm saying solution. That's right. Is equal to, I taught you, inv of A, that's right, multiplied by vector B. Here we go. That's right. It's gonna be this number. Is this right or wrong, guys? You tell me. I give you 2 seconds and I'm gonna freeze it. Okay, guys. I hope that you thought that. Okay, guys. So, obviously it's wrong. Because why? Because of our B is different from what I said. That's right. So, A is 1, 3, 5 again. Okay. and actually we have it. That's that we have this, right? And now solve is equal to, okay, inv A multiplied by our B, which is 1, 4, and 16, because must be 3 by 1. And here we go. So we get that this is your X, this is your Y, and this is your Z. Understand? So we solved the problem. In the previous case, because I loaded B was the previous P from the previous problems, right? So you have to be very careful. Understand? So because sometimes the data, because data is being saved in the workspace, you have to be very careful that when you're working in the workspace, you don't give a wrong number. And that's it, guys. So I'm going to continue this topic about practicing and then the other topics.